Hi everyone, I'm Professor Bergasser, and in this video we're going to be looking at two more quantities for rotational motion, and that's rotational energy, rotational kinetic energy to be specific, and rotational momentum, or angular momentum. We've seen energy and momentum in the translational sense, and seen how they've been used to solve for different kinds of problems. For example, for energy, where we can look at how forces act over a distance. And for momentum, how forces act over a given amount of time. That's our impulse. We'll see equivalents for the energy work and momentum impulse ecosystems that apply also in rotational motion. And we'll also see that we have conservation laws that include rotational energy and angular momentum as well. Now again, as a reminder, we've got all of these parallel quantities that we're starting to build up between the translational quantities, velocity, acceleration, mass, and force, and our rotational quantities, which include angular rate, angular acceleration, our moment of inertia, and torques. And of course, these are interrelated with each other, particularly through the forces. The torques are just the position cross force, and that gives rise to an angular acceleration. Whereas the regular force gives rise to translational accelerations. Now, we could try just a simple substitution to see if there are equivalent quantities for rotation based on what we know for energy, kinetic energy, and momentum for translation. So for kinetic energy for translation, we have 1/2 mass times v squared. And remember that in our comparison, the equivalent for mass was the moment of inertia, and the equivalent of velocity was the angular rate. So if I just substitute those in, I get an expression for the kinetic energy of rotation, which might be right. We'll see in a moment. Similarly, for momentum, I can substitute moment of inertia for mass and angular rate for velocity, and we can get potentially an expression for the angular momentum, which here I've defined as the letter L to meet with convention for rotational angular momentum. Now, are these right? Well, it turns out, yes, in fact, these are the equivalents of kinetic energy and momentum from an angular perspective for rotation. But let's see how we get those more formally by going back to our model of a spinning object. So if I just take a wheel, and here the wheel is spinning around in this direction, so the angular rate vector is pointing out of the screen, right out at you. If I look at different pieces on this disk, we could say they're scattered about in different places on the disk. We can calculate what those velocities are, the actual linear velocities, as they spin around. And that, of course, is just the radius times the angular rate. The further the object is from the center of rotation, the faster physically it is moving as it spins around. Now, how do we relate this back to kinetic energy? Well, let's calculate the calculate the translational energy of each of these little pieces and see how that relates to the rotational energy. Well, that's just adding up 1/2 times each of the individual masses on our disk times their speed squared. But of course the speed is just equal to the radius of the object away from the center of the circle or rotation axis times that angular rate. And of course that angular rate is the same for all of the pieces because that's a solid spinning object. Well, if I just group these terms a little bit more carefully, we'll notice that in the middle we get a term that's equal to the sum of the masses times their perpendicular distances squared. That's just our definition for the moment of inertia. So substituting that in, we indeed get an expression for our kinetic energy of rotation, which is 1/2 times the moment of inertia times the rotational rate squared. And again, this is a scalar quantity, just like the kinetic energy of translation is a scalar quantity, and it is going to be greater for the faster we rotate the object, and it's greater for if we have a larger moment of inertia, which of course means the mass being further away from the rotation axis. Now, it turns out kinetic energy of rotation is something we have to include in our total kinetic energy for a system. If we have a spinning disk such as this, the motion of spinning is energy. There is energy you have to put in to that object to make it spin around. So when we actually add up all of the kinetic energy of an object, what we're really adding is the kinetic energy of translation of the center of mass of the entire object, plus the kinetic energy of the object about its center of mass. Those two motions combined give rise to the total kinetic energy of the object, and that's just equal to 1/2 mv squared plus 1/2 I omega squared. Now, another thing we've seen for kinetic energy is that the change in the kinetic energy, at least for translation, is just equal to the dot product between the force and the displacement. So it's the component of force that's acting along the direction of displacement. When you multiply those two numbers together, we end up with a change in the kinetic energy, a work done on the object. And of course, if the force is acting along displacement, it will add kinetic energy. If it's acting against displacement, we'll reduce the kinetic energy, we'll slow the object down. Well, it turns out we have exactly the same kind of expression for our kinetic energy rotation. The change in the kinetic energy rotation is just equal to the rotational work. In this case, as opposed to force acting over a displacement, it is the torque acting over the angular displacement. So if I have, again, my object here, if I apply a torque in the direction of the angular displacement, how it's being moved around, of course that's increasing the kinetic energy of our object. So in much the same way, the direction of these vectors matter. As long as I apply a torque in the same direction of displacement, I'll get more rotational kinetic energy. If I apply a torque in the opposite direction, I'll get less, and I will reduce my kinetic energy. Now, there is such a thing as rotational potential energy. Recall that one way of changing the potential energy for translation is just to apply a force that's a conservative force, and that energy gets kind of stored in that sort of conservative force field. So it turns out we can have similar kinds of conservative rotational forces, or conservative rotational torques. A good example is just a torsional spring, like one you might see in a mousetrap. As you pull this spring back, the amount of angle at which you're displacing this spring is going to increase the force of it wanting to come back, that restorative force to snap right back. So that's a perfect example of a spring law. In fact, it is a spring because it's a torsional spring. And so you can write down the torque as minus some constant, which is that torsional spring constant, times the angular displacement. And using that, we can compute the potential energy for that spring. And it turns out it's almost exactly the same form as we had for our translational spring, 1/2 times our constant times the angular displacement squared. So in the case of rotational motion, we can always store some of our energy into rotational potential energy just as much as we can store energy into translational potential energy. Now recall for translational energy, we also looked at the total mechanical energy as the sum of the translational, kinetic, and translational potential. Now we've got these other terms for energy in rotation. So we have to redefine our total mechanical energy as the sum of all of these terms: kinetic energy of translation, kinetic energy of rotation, potential energy of translation, and the potential energy of rotation. All of these add up to be the total mechanical energy. And as we saw before, in the absence of any dissipative forces or dissipative torques, and of course those are torques that arise from the dissipative forces, then the change in this total mechanical energy of our system is equal to 0. And this is a very powerful approach because we can see how, for example, the coupling between different motions, for example, translation to rotation or potential energy down to both translation and rotation, that exchange of energy within our system can occur, but the total sum of all of the energy across this sort of event or transition is going to be equal to 0 as long as there's no dissipative forces. So this will be a way of looking at how maybe very complicated interactions occur over a certain distance or over a certain amount of rotation. As long as there's no dissipative forces, you can always appeal to the sum of the energies being equal in both cases. The change is equal to 0. Now there are of course cases where we have dissipative energy, and this is where we apply our work energy theorem and just calculate the work done by the dissipative forces. In this case, though, if we're looking at the total mechanical energy that includes translation and rotation, we have to include the work done by dissipative forces in a translational sense, that dissipative force dot the displacement, plus the work done by dissipative torques in a rotational sense. So that's all the dissipative torques dot the angular displacements over which they act. Now, it'll turn out, as we'll see some examples of this in another video, that sometimes what we would normally have as energy going away from the system through the translational work, dissipative work, might actually be transformed into positive energy going into the rotation, for example, spinning up an object as it rolls down a hill. So as we add up both these terms, you may find that in fact we get some additional energy put back into the system through these dissipative forces because they act more as a translator between one form of motion, translation, into rotation, and vice versa. So let's look at our other rotational quantity, angular momentum. And we're going to look at this schematically in the same way that we did with energy, looking at our spinning disk here that's rotating around with an angular rate that points out from the screen. We can again break this disk down into sort of individual pieces and look at their motions, their velocities as they spin around. And again, the velocity or the speed is equal to the radial coordinate times the rotation rate. But we can also include a direction here because the velocity is going to point tangential to the circle in which the object is spinning around. So we can add up all of these different vectors, and if we multiply them by mass, we get all the individual momentum, the translational momentum of each of these individual little pieces. Now, if I want to look at the total momentum of this system, this rotating system, I just have to add up all of those vectors. But notice that something that happens here when I add up the vector that's pointing off in this direction. That exactly cancels the vector that's pointing off in this direction down here. Those vectors are equal and opposite in direction, so when you add them up vectorially, they're equal to 0. Same thing with our opposite sides on the side here. In fact, if you add up all of the momentum going around the radius here of the circle at every piece, as long as it's a symmetric object, we're going to find that all of these momentum cancel out. Now, this is not a surprising result because, of course, we only have a spinning object, not a translating object, so we should not expect there to be a net momentum to the source, which is translational. But how do we encompass this sort of rotational oomph that this object has as the masses spin around? Now, hopefully you see what I'm doing. I'm kind of doing a cross-product right-hand rule thing, and in fact, that's how we're going to define our rotational momentum. As opposed to just the linear motion, we're going to calculate it as the r cross p. So r across the individual momentum is our angular momentum. And notice this is very similar to how we defined our torque. The torque was the radial coordinate cross the force that's being applied. And of course it's important that those coordinates, those two vectors are perpendicular because that perpendicular force is how we get things to spin around. So spinning motion is just the radial coordinate cross the linear momentum, and it has slightly different units for momentum because of this extra r factor, so its units are kilograms meters squared per second. Now, just to see how that adds up, if we now calculate all of the torques as opposed to the momentum, or sorry, all the angular momentum as opposed to the momentum of all the pieces, this is just adding up all of their radial coordinates cross momentum, and because these velocities and momentum are perpendicular to the rotation axis, you don't have to worry about the angle between these two. They're always going to be perpendicular. So we just get r times p, and of course p is just mass times velocity. But velocity is also equal to the radial position times the angular rate. And if you look at our equation here, you see that again this term, the sum of the masses times their perpendicular position squared, added up together, that's the moment of inertia. And we get an angular rate and a direction that points in the direction of our angular motion. So indeed, we have confirmed that the angular momentum can be written as just substituting mass, substituting moment of inertia for mass and angular rate for velocity, and it's a vector quantity, much the same way that regular momentum is a vector quantity. Now, previously when we looked at translational momentum, we were able to relate the change in the momentum with respect to time, the change rate, and that turns out to be exactly equal to the force. In fact, this was Newton's original derivation for force. It's the change in the momentum with time. And it's a vector quantity, so it points in the same direction as the force. Turning around, we can write down just the total change of momentum as just the force acting over some amount of time. Well, this was our momentum impulse relation, and you shouldn't be surprised that we have an exactly equivalent momentum impulse relation from a rotational sense. So when we look at the change in the angular momentum with time, that's equal to the moment inertia times the change in the angular rate with time, and that's just the angular acceleration, and that's just torque. So we get exactly the same parallel construction between the force and change in momentum and the torque and the change in angular momentum. And we also get the same angular impulse. A change in the angular momentum of a system or an object is just the torque acting over some amount of time. Now, one of the great things about having momentum in the first place is we're able to apply this idea of conservation of momentum. If we define a system and look at only the external forces acting on the system, in the absence of external forces, we can say that the total momentum of that system is unchanged, it's constant. And we're able to use that to solve for lots of complicated internal interactions where we don't have to worry about the force of the internal actions, just the initial and final states, because those of momentum have stayed constant. Well, we have exactly the same expression for angular momentum. In this case, we're looking for any external torques. If there's no external torques, we can add up the angular momentum of all the components in our system, and that total angular momentum is going to stay constant no matter how those individual objects act within the system. It only depends on the external torques. Now, it turns out that this is a much more powerful conservation law because it's often the case that even if we have external forces acting, we may not have external torques because many of the fundamental forces in nature are centric to bodies. Think of gravity, which acts on the center of mass. That won't cause rotation on a system if it's applied from an external perspective. So it turns out that it's more often the case where we see conservation of angular momentum than we necessarily conservation of linear momentum. And as long as we can find there's no external torques acting on a system, we can use that to solve for the motion of a system despite the complexity of the interactions within that system. Now, a great example of this is, a sort of classic physics example is the case of an ice skater. It's also true for divers or gymnasts or anyone who flips around and spins in their own axes. When you have your arms out to the side, you have a very large moment of inertia. Your mass is far from your body. By bringing those arms in, you're reducing your moment of inertia. Now, this interaction involves all sorts of contractions of muscles and cells and energy transfer, but if we choose a system in which I am isolated at least from external torques, this process can allow me to spin up faster even without actually having to apply any torque within the system. So this just comes directly from conservation of angular momentum. The initial angular momentum with the arms out is some value. The angular momentum with the arms in is another value, and those values are the constant as long as there's no external torques. So equating those to our moments of inertia, we can find that the spin rate will increase as long as the final moment of inertia is smaller than the initial moment of inertia. And this is used all the time for all sorts of various spinning activities. An example of angular momentum conservation that you may be less familiar with but is still important in your daily lives is the Earth-Moon system and its angular momentum exchange. The Earth and the Moon are very far from the Sun, so we don't feel any external torques, not much in the way of external torques from the Sun, but there is torques acting between the Earth and the Moon system. The Moon pulls on the Earth, and it pulls particularly the fluid parts of the Earth or oceans out, and those oceans get pulled away, so we end up with an asymmetric body, these tides that happen twice a day. And it turns out because the Earth spins every 24 hours, which is faster than the 1 month cycle of the Moon, those tides are slightly offset from the orientation between the Earth and the Moon. So this offset asymmetric body causes a torque, a net force to act between the Moon and, say, the near side of the tide. And of course, anytime you have a force acting from one object to another, you're going to have the equal and opposite force acting in return. Now, this complicated force that depends on the distribution of the tidal mass in the Earth and the distance of the Moon and the size of these bodies, that's an internal torque interaction. And we don't actually have to calculate what that specific value is if we're treating the Earth-Moon system as isolated from any external torques. Now, the way these forces work, the Earth is actually speeding the Moon up in its orbit, which is causing it to move further away. At the same time, the Moon is pulling the Earth back in its rotation. And we can see this in the angular momentum. As the orbital angular momentum increases, it's going faster and at a larger distance, we have to get that angular momentum from something else. And that something else is reducing the angular rotation rate of the Earth. Now, do we see this happening? Well, indeed we do. Every few years, the U.S. Naval Observatory has to add a second to our official time because what we have classically called a second is actually changing because our day time scale is changing as we slow down due to this Earth-Moon interaction. In fact, there's lots of evidence that the Earth's day was significantly shorter in the distant past because of this interaction. So we experience this internal torque interaction all the time, although it's very hard to see on a human scale. But it's something that we can very accurately measure, and it's something that we can easily calculate thanks to this conservation of angular momentum. So to summarize, we've got these two additional quantities for rotational quantities, kinetic energy of rotation and momentum of rotation, or angular momentum. And they have identical expressions to our translational forms, just substituting in our moment of inertia for mass and our angular rate for velocity. And just like kinetic energy for translation, there's a kinetic energy of rotation that has a work term. Change of that is due to work. There's also potential energy of rotation. And the total energy of a system is the sum of all of these energies: translation, rotation, kinetic, and potential. For angular momentum, we have the same kind of impulse relation. The change in angular momentum is due to torques acting over time. And as long as there's no external torques to a system, the angular momentum of that system remains constant. And that's a very common thing that we see in all kinds of systems in nature, because it's difficult to have external torques, with many of our forces being central forces. So we'll see some examples on how to apply these angular energy and angular momentum expressions for solving all sorts of different problems in some of the upcoming videos.